So today's presentation is part of our professional development seminar series. These are classes that are offered by Generac, reviewed by and approved by the Milwaukee School of Engineering. And these classes are classes that we offer both via webinar, something like this, as well as something that we were able to provide, face to face in your office if you wish. They're generator specific classes. There's about 20 of these classes. They run about 45 minutes, and they cover all kinds of different topics. Today is paralleling concepts. So this is part one of our paralleling presentations. Part two, GPS 325, gets a little bit deeper into onboard paralleling of generators, how we parallel generators, medium voltage paralleling of the systems. So this presentation will talk at a high level about paralleling concepts. When do we deal with paralleling concepts? Why do we deal with them? Again, as Tyler mentioned, my name is John Sharp, and I'm the Director of National Power Solutions for Generac. I've been with Generac for 14 years. Before that, I did 20 years in the Caterpillar dealer network. So I've got 30, 40 years of experience spending time in the generator world. Again, if you have any questions at the end, please feel free to fill them out or fill out through the chat as we go along, and we'll be able to address those. So let's get cranking in here and get into paralleling concepts. So like I said, this presentation gets into a bit of the high level of dealing with paralleling. Why would you parallel? Different methods of paralleling. Talking about grid paralleling, talking about paralleling requirements, synchronization, what type of protection would you be required, and gets into the sequence of operations. In the second presentation that we offer, we talk more about specifics to gen-to-gen paralleling, how you do it the traditional way that's been done for years with paralleling switchgear versus the integrated methodology that's been around now 20, 25 years. Talks of comparisons of different types of installations and how we deal with medium voltage options. Okay, so getting into generator to grid paralleling, we're going to talk about three different methods here. I'm going to talk about momentary paralleling, that's closed transition transfer switches, soft loading, and long-term grid paralleling. Okay, so most of you would know this, right? In a typical transfer switch, we talk about transitioning between the generator and the utility. We talk about what's done as an open transition transfer switch. That is when we have a break before make. We are going to separate ourselves from one source before we transition to another source. This particular switch, what's known as a CTTS, or closed transition transfer switch, is the opposite of that. It's where we're going to go ahead and we're going to take two hot sources, and as we transition from one source to the other, we're going to go hot. We're going to make with the second source before we break from the first source. So it's a hot to hot transfer, and it is a complete overlap of the power. So there is a moment in time, somewhere between 50 and 100 milliseconds, where both sources of power, in this case, typically a generator and a utility, will be tied together. Okay. The benefit of doing this methodology, and recognize that this methodology is something that you would see on a regular day, is when you would see the return to utility after exercising a generator or after losing power, right? This does not prevent you from losing power. An unexpected outage is an unexpected outage. It's a matter of unexpected outage, start on generator, transition to generator. But now when I'm transitioning back from generator, one hot source, to the utility, another hot source, it's going to be a seamless transition between the two. It is going to be a closed transition as we transition between the two. We're going to do this with a method called in-phase monitoring. And in-phase monitor it's passive synchronization. We're going to look at the sine wave of the generator. We're going to look at the sine wave of the utility. And ultimately, the utility is going to be dead central at 60 hertz. The generator fluctuates a little bit. All generators fluctuate a little bit. And so we're going to wait for their sine waves to get into synchronizations. We're passively just going to watch that. And once that happens, we're going to say boom, and we're going to transition from one source to another. All right, so that's what we call closed transition, or momentary closed transition. Why would we do this, right? Why would you do this? In general, this probably costs twice the cost of a standard open transition switch. So it's not something that someone would do lightly. The key here is the lights don't blink. So why would I do this? The principle that we see most of the time when people are doing this is they're doing this because they're going to utilize their generator for more than just a standby piece of equipment. Or they've got it as strictly a standby piece of equipment, and they just want to make sure that they don't have the lights blink as they transition back. Okay, so we have customers who will do things where they have the generator and they will use it for some level of economic dispatch, be that it's some sort of demand response or curtailment program, peak shaving, and that type of thing. And so this allows the customer to transition to two hot sources if they're going to be running the generator more frequently, right? Most standby generators, generator exercises once a week, once a month. It's on Tuesday at 6 in the morning. No one really notices, right? It does its thing out of sight, out of mind. But when you're dealing with economic dispatch, that can happen in the middle of the day. You don't want to disturb the work that's going on within your building, either just the lights blinking or computers going or a manufacturing process where you may have to shut things down as we transition across. This way, we get a seamless transition between the two and don't notice anything. Couple things to think about when we deal with closed transition transfer switches. There is a likelihood of not zero that these two sources could get stuck together. Right? I've got two contacts and I've got one closed. I'm going to close this one before I open this. Yes, there's a possibility that somehow this mechanism, however slight this possibility is, could get stuck in between, and you would have both contacts closed. In a case like that, these switches have built-in protection timers to be able to then send a contact to either the feeder breaker that is feeding it from the utility or the generator feeder breaker to be able to take that source offline so that we no longer have two sources feeding the load. Okay, so that's a conversation you want to have with an engineer or whoever is designing this. Say, hey, if we're going to do closed transition, totally on board with that. But we need to make sure we understand if things went wrong in this minuscule possibility that it goes wrong, that we need to separate from one of the two sources. We can't keep everything tied for a long term. Which one are we dumping? Right. So do we need shunt trip on the breaker that's feeding it from the utility or from the generator to make sure that we get off of one of those two sources? Okay. Something else you may want to discuss is to talk about utility yourselves. Some utilities are perfectly comfortable with the functionality of a closed transition switch. They recognize that this is a pre-designed, pre-manufactured product. They're very reliable. Like I said, the likelihood that they would get stuck together is very low. But some utilities don't accept that and would say, listen, they want some level of protection, some level of redundant protection outside of this protection timer. They're going to want maybe a reverse power relay at 32R. In my career, I used to cover the Raleigh, North Carolina market, the Eastern North Carolina, and I covered both Eastern North Carolina, which was under Progress Energy at the time, and Duke Power, which is who's covering it all now. And Duke Power absolutely closed transition insisted on a reverse power relay. So we always had to put a BAS or 32R relay within the transfer switch, whereas Progress Energy didn't care. Right. So closed transition in one town was different than closed transition in another. So do make sure that you check with your utility to make sure of their requirements. Even something as short as 100 milliseconds, they may ask for a level of protection within the device. And you can usually get those devices installed within the transfer switch as a standard option. Okay. Now, that is a closed transition momentary under 100 milliseconds. However, sometimes this transition is a bit challenging for the generator or for the utility. We think about this, right? I'm transferring between two hot sources. So maybe I've lost power. I'm on generator. Been on generator for a couple of hours. The building's back to running perfectly normal. And now I need to transition back to utility because the utilities come back. Okay. When you make that transition, we're not shutting off any loads, right? Like I said, it is a smooth transition or closed transition between the two. So if the building is running at 300 kW or 500 kW of load, when we hop over to back to the utility, that's 300 to 500 kW of load that's going to hit, boom, in 100 milliseconds onto the utility. Some utilities are not prepared for that. Also, right, if you were doing some sort of testing or you were doing a curtailment program, demand response, anything like that, I'm starting the generator and I want to transition to the generator. Same, right? I've got 300, 500 kW of load sitting on the utility and I'm going to immediately put that onto the generator. The generator is going to get a very large block load. When a generator gets a large block load, what you typically see is some sort of what we call a transient response. Voltage is going to dip, frequency is going to dip until we can recover voltage and we can recover frequency by getting enough fuel into the engine. Some people don't care for that, especially if you're doing it on a daily basis or weekly basis. And so to minimize the impact of the block loading, what they've introduced into the market is something called a soft load closed transition switch. So very similar in the fact that it is a switch that's going to be closed transition, but it is going to have provisions to be able to allow you to have those two contacts, or in this case, two circuit breakers closed for longer than 100 milliseconds, right? This may be 5 seconds or 15 seconds, long enough for us to either ramp up the load onto the generator or off the load onto the generator. And then the utility doesn't see a shock, the generator doesn't see a shock. Okay, we all understand this. I'm going after 100, I'm going over 100 milliseconds. So at this point, I'm in eternity when it comes to utility time, right, with electrical time. And at this point, absolutely, utilities are going to want to have a conversation about your utility protection. They're going to want some sort of protection to make sure that as these two sources are tied together and that we're shifting load from one to the other in a smooth, soft load transition, that we're not pushing back on the utility. The big thing they ask for now is they ask for some sort of multifunction relay that's going to protect the utility. Schweitzer SELs, it's 751 relay is what I see the most. Not a commercial for Schweitzer, but just to say that's the relay that I see the most, is something to be able to protect the utility. You need to meet the interconnect requirements of the National Electric Code, NEC 705, and that is typically going to point you to the standard for interconnection to utility, which is IEEE 1547. Okay, SEL used to have a 1547 relay. Today, they just use the 751 feeder protection relay. It has the same functionality. So do check with your utility because there's definitely going to be protective relaying required. Someone is going to have to do a fault study to make sure that those relay settings are good and to the acceptable to the utility. So just understand, once I make this leap from an out-of-the-box closed transition switch to a soft load switch, I'm going to a more custom piece of equipment with some custom protection and something you've got to work out with the utility, because once I'm over 100 milliseconds, I might as well be on here for 10 years. I might as well be on there for eternity. The utility is going to want to have something to say. Speaking of eternity, we do have other programs that you see out of the marketplace. One particular one is called peak shaving, right? In that particular case, that is where we are dealing with the demand charges that the customer is seeing from the utility. And on days where the customer is going to be using a lot of energy, right? A lot of, they're usually only use 300 kW a day, but today they're going to be using 500 kW because they got a lot of testing going on of some equipment or some other process. We want to minimize this impact of the peak because that's where the utility is going to be doing a lot of billing. And I mean, I've seen places where it's $20 to $30 a kilowatt of demand charge. That's quite a bit. And so this is an opportunity to run the generator and just take the peak off. You're not going to take the whole thing, but at least if you want to stay at 300, stay at 300, and anything over 300, the generator is going to eat. Okay. Base loading, a little bit of the opposite. This is where the customer is saying, hey, I'm managing my own power spend and fuel costs are getting pretty high. Utility on the spot market right now, utility charges are very high. And so I've got a generator on site that is emission certified to allow me to run more hours than just standby. It's cheaper for me to run my generator today and to power my facility, base load my facility. And so it's just cheaper for me to make power on my own versus getting it from the free market. Okay. And then I'm going to so I'm going to base load the unit. I'm going to say, all right, give me 75% load on this piece of equipment. And then anything that goes above that is going to come from the utility. So you minimize your energy spend. So you look at the two different parts of a power bill. One is minimizing demand, right? KW. The other is minimizing KWH, which is energy consumption. Those are two methodologies. And both of these require the generator to be tied to the utility for extended periods, multiple hours. You don't see this every day. One of the reasons you don't is something I mentioned has to do a lot with the EPA. The EPA rules are going to limit what products you're allowed to tie to the utility in extended version. You also have to look at the utility. How friendly is a utility about letting you do this type of thing? They're going to have different types of standby charges and things like that that are going to make this, maybe the payoff don't work as well. So you've got to make sure that the utility and economics are going to work to go down this road. I will tell you that I mentioned that transfer switch is 2 times the regular cost. This soft load transition switch, which is the same as I would use for base loading or peak shaving, is probably 4 to 5 times the cost of a closed transition switch. So it is a custom piece of equipment, not something you're going to buy every day. The economics, the dollars and cents really need to be worked out. So base loading and peak shaving hasn't been that common in the U.S. We've seen it a bit more with a lot of the energy shortages we have with AI data centers kind of sucking up all the power. So you do see that, but recognize that there are emissions rules that are going to get in your way. If you're doing a diesel unit, it has to be the cleanest diesel unit you can buy, because now you're doing more than just emergency service. You're now providing an economic benefit, and the EPA says you're going to have to spend money to make money, so you have to have the cleanest piece of equipment out there. Natural gas generators lend themselves a little bit more. They have lower maintenance costs, lower fuel costs. And there's something that we see more frequently in these types of applications, but this is what you would face based on the 2 different types of fuels that we primarily see in the marketplace. Okay, generator to generator paralleling. So we've talked about paralleling and synchronizing to the utility. Let's talk about gen to gen for a little bit. Okay, so what is a paralleling system, and why would you do a paralleling system, right? What we're talking about here is tying multiple sources together to be able to use the benefit of building blocks, right? You usually parallel generators for one of 2 reasons. You're either trying to increase your generation capacity, or you're looking at doing some sort of redundancy. Okay, so in the case back here, I've got 2 500 kW generators tied together. That gives me 1,000 kW of capacity. However, when I jump over here, now I've got, 6 1 megawatt generators together. We start talking about potentially being a redundant source, right? We're trying to improve reliability by providing levels of redundancy in the equipment. And a single generator in and of itself, and it depends on who you talk to. The Uptime Institute has their opinions. They think a generator is about 94% reliable. Generally, the industry sees a generator as being somewhere around 98%-ish reliable. So, and it doesn't matter the brand, right? It doesn't matter what color it is. It can be yellow, it can be green, it can be gray. Doesn't matter. If you don't maintain that piece of equipment, the reliability of that piece of equipment drops. So it's really on the customer to be paying attention to the maintenance program, cleaning their fuel, making sure their generator is ready to go. Otherwise, it doesn't matter who you bought it from, thing's not going to run. So having the opportunity to add additional generators for an N+1 reliability or N+2 reliability makes the customer much more comfortable, because they know, heck, even if 1 generator doesn't start or 2 generators don't start, that you have the ability to make sure you're still covering your necessary loads. Right. Other reasons that we would talk about using a generator paralleling system. So I talked about capacity, I've talked about reliability, but you also have scalability, right? You've got a building that you're building, and you want to be able to back that building up, but you've got an option where you're saying, well, if business goes well, I'm going to be able to increase the size of this building. I'm going to add onto this building, or I'm going to build a second building on this property, or whatever I'm going to do. But I don't want to spend all of my capital on day one to make sure that I have generator capacity. By going with a scalable solution, you can say, okay, let me buy what I need today. And then if the business plan works out 5 years from now or whatever, then I'm able to then just buy additional capacity. As long as I've got the infrastructure already sitting there, it's a matter of just, adding additional generators to give me more support and capacity. So scalability is another method. The last thing we talk about serviceability, especially if you're serving NEC 700 type loads. Okay. You want to make sure that 10-second load is going to be backed up all the time. And I've still got to change oil. I've still got to change filters. I've still got to clean the fuel system, everything along those lines. But I don't want to take the whole system off in order to do so. If I have 1 single generator and it's down for 4 to 6 hours, I'm not protecting the 10-second loads, or I'm not protecting my data, or I'm not protecting my facility while the oil is being changed. A scalable solution where we're adding generators to it allows me to maybe shut one generator off, but leave another one online so it is prepared to support the critical loads when I need to. Also, going back to National Electric Code NEC 700, where it calls for roll-up connection boxes. The standard says if the load is being backed up by a single source of backup power, you have to bring in a roll-up connection box. However, if you have multiple generators that are capable of feeding the critical load, the NEC 700 load, you are not required to design in or utilize any sort of roll-up connection to back up the system while you're changing oil or maintaining the product. So I get the level of redundancy and security and serviceability for those components while I'm bringing a unit down. I know that I'm still supported. Okay, why wouldn't I use a paralleling system? Well, there's a couple different things here. The first thing is to talk about what type of paralleling system would I have. In this particular case, what I'm showing you is what we call a traditional paralleling system. It's where it's going to be paralleling switchgear. And the biggest problem with paralleling switchgear, it's expensive. Right? It's also big. What I'm looking at there is probably 10 feet wide, 8 feet tall, at least 4 feet deep. So do you have the room for this type of equipment in your electrical room within the facility? And if not, that's a challenge. Also, you look at it from a complexity standpoint. Paralleling of generators in this particular methodology, where the intelligence to do so is in a piece of switchgear, that becomes a custom event. Right? It's customization. All the pieces of paralleling switchgear are going to be custom to the job. And that's a little bit challenging because you know that you've always had this one piece of equipment that's in the building where there's a limited number of people that can service it because it's a custom piece of equipment. So why wouldn't you do that? Paralleling switchgear, again, can be expensive. It's got its place. Do not get me wrong. And I've put a lot of systems in the market. But understand that there are challenges to having a traditionally paralleled system. Okay. Now, what is required to parallel generators? Let's dive a little bit deeper from a technical side. Okay. I can't just take this generator and that generator and tie them together. Right? I've got to make sure that there is enough commonality of those products. And the first thing we talk about is are we going to be able to control those components with the same brand controller? Best way to put it, brand, right? When you are tying generators together, the paralleling controller, the controller that's going to do the decision making on each of those generators, needs to be fully compatible with the other. They need to speak the same language. They need to interface to one another. They need to work the same. And that's not always the case. If I buy brand X here, brand Y there, getting them to tie together isn't quite going to work because they don't talk to one another. So the first thing is I've got to have commonality in controls. And along with commonality controls is because I have to be able to adjust the speed and adjust the voltage of the products, right? So I've got to have that commonality as they speak to one another. Other technical things regarding the generators, right? We have to make sure that the generator itself, the windings inside the alternator, or what we call the pitch of the alternator, that they're the same. Most people in the industry use what is called a 2/3 pitch alternator. Virtually every manufacturer does that. There's one manufacturer that has some products that are not 2/3 pitch, and it's a challenge to take a non-2/3 pitch and make it parallel to 2/3 pitch. So you got to make sure those are the right. You also have to have the same number of phases. You can't parallel a single phase with a 3-phase. You can't parallel 208 volt with 480 volt, right? They have to be the same voltage, the same phase, and phase rotation. In this case, most generators are ABC rotation, so that's not as much of a challenge, but it is a requirement, right? I can't have one unit spin in one way and one unit spin in the other and get them to tie together. That's not going to work within synchronization of the generators. Okay. Next, what I need equipment to parallel. Not only do I need a controller that's going to do that, but I need what I'm going to call a synchronizing switch or paralleling contactor. Some will use a circuit breaker for it. I need some device that I can open and close as I try to tie these two together. We'll go through a sequence of operations in a little bit, and it'll make more sense. But I have to have the ability to open and close this device to tie these two. If this one's already on board and already running, it's also hot to here. This generator's got to tie to that, and so I need a device to be able to make those happen. Okay. How are we doing that? Well, the first thing we have to do is we have to synchronize the pieces of equipment together. We need to electrically lock them together. That means they need to be running at the same voltage output. They also have to be tied together at the same speed. Okay, so the first thing we're going to do is, you can see generator 1 that's already on the bus has got a particular voltage. Generator 2 has a much lower, so I have a phase voltage mismatch. So the first thing I've got to do is I've got to increase the excitation of the second generator so that now my voltages match, right? If one's 480 volt, the other one needs to be 480. Okay, if one's 481, that second one needs to be 481 as well. You need to tie those voltages together. And then we're going to adjust the speed of the second unit so that these two sine waves start to lock in. So this is, previously I'd used the term passive synchronization. This is not passive. This is 100% active synchronization. We are going to control generator 2 to make it match and mate up to generator 1. And once we do that, we're going to close a device that's going to lock the two together. And once they're locked together electrically, that's a very, very strong bond. Okay. There are different devices that you can use. If I look at these two different things going on here, right, this is traditional paralleled, and they use circuit breakers to tie these together. Nothing wrong with that. Let's go ahead and use a circuit breaker. This particular one that we've got here, this is what we call an integrated paralleling, something we talk about in our next class. This is a contactor. This is just a motor starting contactor switch, and serves the same purpose as the circuit breaker. It doesn't have overcurrent, but in this case, I'm not asking for overcurrent. I've got an overcurrent device sitting here. So this is just the device I'm telling it to close as quickly as I can so that I can lock these two devices together. Once the two devices are together, we need to be able to balance the load between the two. Okay, so this is what we call load sharing. We want to make sure that both generators are putting out positive amounts of power in relation to what they can contribute. Okay, what I'm getting at here is, you can take a 1,000 kW generator and you can parallel it to a 500 kW generator. And if we put 600 kW of load, we're not going to put 300 over here and 300 over here. That's not load sharing. It's going to be load sharing based on its ability to contribute. Okay, so this one's twice as big as that one, which means I'm going to put 400 kW on the 1,000 kW. I'm only going to put 200 on the 500. That's making sure that we balance the load proportionally to how much they can put out. Okay. That is done primarily through the load share methodology built into the unit, where we are adjusting the output of the voltage regulators to make sure the units stay synchronized together, have consistent output, and then we're controlling the fuel to make sure that the fuel is consistent with the ability to push it out. Right. So we're going to adjust the voltage regulator. The term I'm going to use is called biasing. I'm going to bias the voltage regulator, and I'm going to bias the governor to make sure that they're both putting out what they need to put out to be able to contribute to size of the piece of equipment that they're attached to. Okay. What I'm looking for, if I'm looking at the power triangle here, is I want to make sure in normal operations that I have positive kW, right? That's from the engine. That's fuel burning. And I've got positive kVAR. That's going to come from the voltage regulator. So make sure that both units are pushing positive energy out, right? I don't need negative energy, so I'm an underexcited unit where one unit is not putting out the power that it needs to. And I certainly don't want to be in this area here. In this particular area where I'm underexcited, I'm in reverse power condition. This is when we talk about what we call motoring a generator. One generator is not only putting out power that's feeding the load, but it's also pushing power back into the other generator and pushing that other generator to run. We don't need that. So we have protection functions that make sure that we're not in reverse power condition or an underexcited condition. And then we're always positive pushing out. That's what that controller, that paralleling controller, is going to do for us. Okay. Within that paralleling controller, there's going to be some protections. As I mentioned before, right? Reverse power 32 is going to be one of those functions. Okay. We're going to have to make sure that we have good voltage on both units. So we're going to be measuring voltage and make sure that we don't have any overexcitation. Like I said, where maybe one unit is powering another one. So one is cranked up to a bit of a higher voltage. So we have protection functions built into the controls. This would happen on any paralleled system, be it a traditional parallel system or an integrated system. What you've got to have is you have to have these protective functions built in to make sure that, one, the system's working the way it's supposed to, and two, if we have an outlier, that we're shutting a particular piece of equipment down so that nothing gets damaged. All right. Integrated paralleling, which I'm going to talk a little bit about, has to do with taking the intelligence and the equipment that it takes to paralleling and bringing it on board the generator. Okay, so we call this onboard paralleling or integrated paralleling. About 25 years ago, if you wanted to tie pieces of equipment together, what you were generally looking at is you're looking at a traditional paralleled system. And as I've mentioned before, those things are everywhere. I've put a lot of those in the field, but they are expensive, they're large, and they're custom. And they're also, we're working off of back then, we were mostly in an analog methodology. So setting up this system was very challenging. You had to spend a lot of time to make sure that you balanced everything together so that the units would work well together. There was some dark magic that was involved. There weren't that many people that were physically capable or mentally capable of making it happen, right? You may have in any particular state 100 generator technicians, but you only have 5 that know how to do it. Right? It was very challenging. What the industry went to is they went to a more integrated control approach, where we said instead of all of these analog controls, let's put it into the digital world. And since processors have gotten better, things have gotten better, we can take one processor that can do all the functions. Right? I can be biasing the governor. Right? I can be biasing the voltage regulator. I can control the fuel system. I can control the generator. I can do starts and stops and temperatures and pressures, all of that, as well as protective relaying within the control panel. It's just the advantage of getting into the more and more digital world and better digital capabilities. Okay. By doing that, we've taken the intelligence that was in that traditional piece of gear out of that gear and put it on the gen. So now the generator has the brains to be able to do it itself. And we only need one more device to make this all work. And that is, I need to take the function that we were putting on that circuit breaker and put it onto the generator itself. Okay, a couple different ways to do that. You can use a motor operated breaker on the generator itself. So you're again taking from the switch gear that motor operated, electrically operated breaker and putting it on the unit. Or I could take, and again, that's something I showed you before, I can take a motor starting contactor and have that be the device. It's a very cost-effective solution for getting there. Electrically operated breakers that are small are pretty expensive, relatively speaking. And so maybe going with a contactor that's an inexpensive device makes things a little bit easier and try to be palatable. What this really did, I'm going to go off on a tangent for a second, but what you realized was that by building in this redundancy and being able to put it on the generator, you now had an entire world of customers available that could not afford paralleling switchgear or didn't have room for it. Paralleling switchgear traditionally was, why did we parallel back in the day? We did it for healthcare for redundancy. We did it for water and sewer for capacity because he had this huge water treatment plant and it was going to take 3 generators to power the whole thing. All right, so that's what traditional methods were for. And there were plenty of customers out there that weren't of the magnitude, that weren't in the millions of dollars that it's going to take to implement this system, but they had as great of a need for redundancy, for scalability as anyone else did. The problem was they just couldn't afford it, right? It's kind of hard if you got somebody who's maybe trying to parallel 300 kW generators that cost, I don't know, $100,000 a piece, and then throw in a couple $100,000 piece of switchgear to get it to go. Like, I need the redundancy, but I can't spend $500,000 to make it happen. I'm a small customer, but I need that. Integrated paralleling allowed you to then just buy the generators with the controls built in and make it a more cost effective. So it opened up the redundancy. And that's really what I show here, right? Is it's all about redundancy at this point. Certainly you'd want to be in this plane versus this plane. So it brought customers who didn't have that opportunity before because they just couldn't afford it. It didn't fit into their business plan and gave them levels of redundancy. I think of a project we have in downtown Philadelphia. It's a grocery store. It's got 300 kW generators. What in the world does a grocery store need to be able to build in redundancy, right? It was kind of like, but I don't know enough of their business plan, but redundancy was a big play for them. They only need 2 of those 3 units, but they bought them anyhow. Again, in my head, I'm going, you're a grocery store, but it was important to them to be able to do that. And so they couldn't have done that with a piece of paralleling switchgear only because they didn't have the room. If they were in the back of a grocery store, there's no room back there. And the cost was prohibitive for what they tried to do. By having integrated systems, it opened up the door for those customers to look at and proving reliability in their whole system. As I mentioned before, scalability becomes a big deal, right? What can we do? This particular facility is a data center. They've got 5 1 megawatt generators, and they've got 6 slabs available to be able to add additional. So they're prepared from a distribution standpoint and a projected load of ultimately 11 megawatts, but not on day one. Right on day one, they're like, you know what, 5 megawatts is going to do us. Probably had about 3.5-ish megawatts of load, and so that built in some redundancy for them to be able to have 5 units to cover what they needed. And then as this data center load continued to grow, they were going to be able to add units to tap into the system. So a scalable solution is always something that you think about. What do I want to spend on day one? What do I want to spend 5 years from now? Okay. And total owning costs becomes a conversation that people get concerned with. Many of you that are listening to this, if you're not familiar with what we're doing here, one of the intuitive things that people say is, how in the world can it be cost effective to have, I'll just use an example. Let's say instead of a 2,000 kW generator, I go with a 4x500 kW generator. Right? So 4 generators, 500 kW piece, all tied together to give me 2,000 or a single 2,000. Like, how can that be a cost-effective solution? That's a fair question. Right? Intuitively, it doesn't work. Right? How does 4 engines work cheaper than 1 engine? And I would suggest to you that, well, one of the reasons that works is we start talking about engine availability. You start talking about scaling within a client or within a vendor, right? The 2,000 kW generator is a 65-liter engine. Very large engine, very large industrial engine. It is not, I'm not saying they're not common, because certainly they're pretty common today, or they're common enough today, but it's still it's a big piece of equipment. And there's only so many people that make them. That means there's only so many people that can supply oil filters and air filters and fuel filters for that particular piece of equipment. So frankly, they can kind of charge what they want to for that product. You take a 500 kW generator, that 15-liter engine that you're looking at, that's a truck engine. That's the same engine that's going in front of my house every day for a heavy haul semi, right? The customers or the vendors that make those engines are making hundreds of thousands, if not millions of these engines a year. So you have this complete economy of scale where, fine, I'm buying a 500, but it's one of a million engines they made that year. I know you can't be bad. You can't make a million engines a year and make a bad engine, right? So I know I've got some certain level of reliability of scale of that product. But at the same time, my cost in $1 per horsepower or $1 per kW is going to be a lot less, right? I did a project in Pennsylvania, 1,500 kW. We had 1,500, and we also said 3x500, and 3x500 was $84,000 less than a single 1,500. Purchasing people didn't understand it until I explained to them again that you've got this. Somebody is building a million of these engines, your pricing is going to be a lot less. Your volume pricing is going to be a lot less. So that's from a capital standpoint. You look at it from a maintenance cost standpoint, as I mentioned, oil and filters and things like that. That 2 meg, 110 gallons of oil, 110 gallons of antifreeze. A 500 kW generator has 12.5 gallons of oil. Right. So 4 500s is 50% of the oil that you would use in a single 2 meg. It's a differently designed engine, right? This is a truck engine. Weight matters. Horsepower and weight matter for a truck engine. So I'm only going to need as much fluids as I need. I'm not a big industrial engine like this 65-liter 2,000 kW, where weight doesn't matter because it's a stationary piece of equipment. So you recognize, one, the parts are going to be more expensive, but two, you may need more of them with a single particular unit. The other thing that we see from some people as we start talking about footprint, I mentioned that grocery store in Philadelphia. Those 3 units are sitting on the roof. Again, it's a grocery store, right? Typically a grocery store, there's just an alley behind it. And that alley, you got to keep that open because trucks are in and out of there all day, unloading groceries and deliveries here and there. There just wasn't room to stick a bunch of generators back there. We're able to put them on the roof because you got that flexibility. A 300 kW gas generator is what that had. Total weight on that system is probably maybe 30,000 pounds for those 3 units, whereas a single 1,000 kW gas unit is over 50,000 pounds. Right, so I got a weight, I got a space, I got a dimensional conversation, and you've got a lot of flexibility when you start talking about integrated paralleling because you can move these units all over the place, right? I've got these 5 units in a row. I've got these sitting on top of a roof. I've got this unit that's going on a roof. This paralleling allows you to go with smaller units that I can put in different places together to fit my design if I'm an engineer. Okay, serviceability, I think I talked at length about that, but you just recognize I can shut one unit down while I can continue to operate the other unit. So I know that my critical loads are going to be supported while I'm changing oil, repairing a unit, or whatever we need. The time when you're bringing in a rental piece of equipment, if you got a single unit and your load is so critical that you got to bring in a single unit, if you've got a roll-up connection box, that's great. If you don't, that's a big challenge. Taking maybe 1,000 kW portable generator and bringing it in and tying it to your building, where are you going to tie it in? You tie it into the main switch gear? Are you going to pull the feeders off of the generator and splice onto those? How do you even do that? Becomes a pretty involved thing to bring in a temporary piece of equipment if you had to. Having that redundancy eliminates a lot of that conversation. Okay, last bit here, I believe, on this presentation. Where am I? My slides. I want to show something to go with just a sequence of operations of how these systems work. This is going to be a 2-generator system with multiple transfer switches. So you can see these 2 gens, 2 transfer switches. Now, one switch is a critical switch. This is my NEC 700 switch. This is the one I care about. This is the one that I care less about, right? This is my equipment switch. So I've got 2 transfer switches and 2 generators to back up the system. The generators are going to tie together to something we call collector bus, or just a piece of distribution gear. Siemens, Schneider, ABB, Eaton, doesn't matter who makes it, right? It's not an intelligent piece of gear. It's just a piece of distribution. Right? So we're running on a normal day. I got 2 transfer switches. Life is good. I'm on utility. And I lose the utility for whatever reason. A squirrel just got burned on a line, or a snake, or whatever. Somebody hit a pole, wherever. I've lost power. The transfer switches are going to initiate generator start, just like they would for a single generator system. Once I get generator start, both generators are running. The generators are going to do something called dead bus arbitration. Again, this happens in all paralleling systems, regardless if it's an integrated system or if it's a traditional paralleling switchgear. Somebody's got to be first to the bus. Okay, so these 2 race. They get to 1,800 RPM. Whoever gets there first raises a flag, grabs the ring, and says, I want to get on the bus first, and I get on the bus. Once I energize the bus, again, notice that I am energized to source 2 on both transfer switches, as well as to the load side on generator number 2. So once this switch throws over, this switch sees that I'm available and says, okay, I got a perfectly good source. It's going to switch over to source 2. However, we have the second switch. And the way this particular system is programmed, we don't want to put the second switch on unless I've got 2 generators. All right, so this becomes a sheddable load based on the capacity of the generation in the system. And this device here, my system controller, is the device that's making the decision to say, hey, you need to wait for a minute. You need to hold on. You don't have permission to go until this guy gets on. Generator number 2 is now going to be looking at this sine wave. It's going to match itself to that sine wave, and when it's ready to go, it's going to pop over. And now the equipment transfer switch is available to pop over because now I've got 2 gens on the bus. Now, if this is a storm, it's been going on a long time, you've been running day to day to day, eventually you've got to shut a unit down to change some oil, right? So when we do that, I bring a unit down. My system controller is going to say, well, I've only got 1 gen on the bus. That means I can only have 1 transfer switch based on the program. So we're going to push this transfer switch to a middle or neutral dead position while we service this piece of equipment. Because my concern is this load right here is what I care about. And if I try to put both transfer switches on this gen, it may overload this gen, and we want to deal with that. So the best thing to do is to make sure that this sacrificial load stays in load shed mode until we get the second unit back. Right? We change the oil. We crank that unit back up. It's going to automatically synchronize. And again, once it synchronizes, we're going to allow the secondary switch here to go back over to source 2. Utility comes back, just like you would in any other project. The transfer switch recognizes that, tells everybody, hey, we don't need to be on source 2 anymore. So first we're going to transfer to source 1, and then we're going to tell the system, go ahead into cool down mode. Once you're running in cool down mode for a while, 5 minutes to let the turbos and the engine block cool down, then we can go ahead and shut these units down. So that's a pretty straightforward 2-unit, 2 priority parallel generator system. This would be no different if it was a traditional paralleled versus an integrated paralleling. All of these steps happen. It's just a matter of where they happen. Okay, so this wraps up part one of this presentation. We do, like I said, we do have a second presentation for generator paralleling. We get a much deeper dive into the actual controls of the unit, how we do load sharing, what's the deal with that. So if any of you are interested in that, please reach out to my friends over at EMC who could be able to set up a presentation to have a discussion about that. We've got a little bit of time left, so I want to go ahead and make sure we have time for questions.
Great. Thanks, John. We've had a couple questions come in. Feel free to continue adding questions in the Q&A option at the top of your screen. For now, let's start with one. When you add paralleling, are there additional considerations for NFPA 110?
No. NFPA 110, as far as the generator is concerned, right, spells out a lot of different things. It talks about like what battery charge you're going to use, how big of a generator, how big of a fuel tank, what bells and whistles like alarms you would have on a control panel, jacket water heater, all of those functions. That is not going to change based on going with parallel systems, right? If you're one unit, NFPA 110, level 1, 2 units, you would still need to be NFPA level 1 type product. Right, so they would still have to meet the same standard, but nothing really changes from that viewpoint. They both together would meet that standard.
Great. Next question is, does paralleling complicate fuel management for either diesel or gaseous engines?
When we talk about fuel, it's so complicate. That's a good question. So, here's the thing about managing the fuel. When you have a diesel piece of equipment, the biggest concern you have is degradation of that fuel and things growing in that tank. And how are you going to deal with that fuel management from that particular product? And what you have the value here is I now have redundancy. So if one particular unit has a clogged fill filter because of stuff that's growing in its fuel tank, I know I've got the redundancy. But as far as maintenance is concerned, you want to go ahead and continue to do the regular maintenance on those. Again, the value is here. I can shut one off and still be backed up while I'm treating it or cleaning the fuel and what we're doing. There is the option of mixing fuels, right? Fuel, if you'll notice, I didn't bring this up, but when I was talking about what's required, right? What's required is same voltage, same speed, size is not a factor. Fuel source is not a factor. Right. So you could take a generator, a gas one and a diesel one, and tie them together. If you wanted to say, hey, I want some perceived security of having fuel on site. I want that diesel unit there with the diesel tank, but maybe my other generator is going to be a gas generator. Okay. They can work together. Fuel doesn't matter. Fuel is a BTU input. Paralleling of generators is an electrical conversation. It is not a fuel conversation. So it's immaterial as far as what fuel is in a particular unit, and you can tie multiple fuels together within the units. That's not a concern from those. You may have to slow the diesel one down a little bit because diesel being a more powerful fuel is usually going to respond a little quicker. Like if they had a block load and they're tied together, they both dip, the diesel might recover a little quicker. So we slow the diesel down. It's not a big deal, but it's just a matter of making sure both units recover at the same time. Did I see another question about 2/3 pitch?
Yes, we had one come up about, the question was, can you talk more on the 2/3 pitch of the alternator? Do all generators have the same pitch? And what are the other pitches? How do they affect the operation of generators?
Okay, so what I'm talking about here is I'm talking about when you have the barrel of an alternator. So I'm looking down the alternator, right? And we're running the windings, wrapping the different windings. If I were to do it at if I did it at 12 o'clock and then I came back at 2 o'clock, a full pitch would be 90 degrees if I went 12 o'clock and 3 o'clock. The industry in general does 2/3 pitch. So I'd be 12 o'clock and 2 o'clock. And what that does is that creates a certain shape sine wave, which reduces the impact. Actually, it eliminates the impact of third order harmonics that are produced by the load and their impact back on generators. So if you think from harmonics, I've got different order, 3rd, 5th, 7th, 9th, 11th, different order harmonics. Because of the shape of the sine wave and the 2/3 pitch, The industry, and I'm telling you this, everybody has gone to a 2/3 pitch alternator, right? Us, Cat, Cummins, MTU, Relco, whoever. Everyone has a 2/3 pitch alternator. It creates a certain shape sine wave. And to our naked eye, we wouldn't even notice the difference. If you had a non 2/3 pitch alternator, the shape of the sine wave would be different. The zero crossings would happen at the same time. The peak would be the same, but how we get there, one sine wave would be maybe a little fatter than another. And the problem would be if I have two pieces of equipment, one's 2/3 pitch and let's say one's 6/7 pitch. Those sine waves are going to be different shapes. So at the zero crossing, I'm cool. At the peaks, I'm cool. The problem is getting there, my sine waves are going to be different. And that means with different voltages, I've got now circulating current. I've got maybe as I'm on the way up, I'm sitting here at 235 volts, and I'm on the way up over here, and I'm only at 230 volts. So I'm 5 volts higher. Well, that's a difference in potential between two pieces of equipment that are on the same circuit. And once you have a difference in potential, that causes current to flow. So you would have what's called circulating current. And that's a big challenge to deal with. We don't want that's wasted energy within the system. All the energy, all the current needs to be flowing towards the load. What I'm getting at here is, I can tell you, Cummins, Generac, Relco, all use 2/3 pitch alternators all the way across the board. Caterpillar, back in the 90s and into maybe 5 years ago, came up with something called an optimum pitch, which what meant they were going to do 2/3 pitch if it was cost effective. And if it wasn't cost effective, they were going to do a different pitch. Because back in the 90s, frankly, we're talking maybe a 600 kW generator. You didn't parallel 600 kW generators. It just didn't happen very often. Right? That was, again, that paralleling switchgear issue, the cost and all that. So if a 600 kW generator was 6/7 pitch, nobody really cared. It was mostly sold as a single unit. So for a number of years, in a cost-effective method, they used different alternators at different size units. Some were 2/3 pitch and some weren't. Okay. And again, I know this having been a 20-year guy with what they were doing. And I've had projects where we had different pitch alternators. You had an existing unit, you got a new one, and they were different pitch, and it was very, very difficult to make that happen. You had to do something like a neutral pitch limiter or something along those lines to help reduce the amount of circulating current going through there. But just a very difficult thing to address was a 2/3 pitch. In one particular project, we took the non-2/3 pitch alternator off an existing unit and bought a 2/3 pitch alternator just to make the system work easier. Okay, so 2/3 pitch, it's not a huge conversation, and it's only a conversation if it's a Caterpillar product. I'm not trying to bash Cat. I'm just telling you this is what they did. And so what you got to do is you need to get the serial number of the alternator itself and roll up to Cat or whatever and say, hey, I need the data sheet on this alternator to know what the pitch of this alternator is, because it will not be written on the data on the nameplate of the unit, but you need to know, right? Because you're going to bring in a 2/3 pitch piece of equipment that doesn't match with that one, and it's going to make life very difficult.
Great. We had one question come in about wear and tear. Is there any part of the controls that tries to even out run hours between generators?
You can have controls that do that. However, I would suggest to you that it's somewhat of an antithesis of why you do the paralleling in the first place. The whole point of the paralleling is you're either paralleling for capacity or you're paralleling for redundancy. Okay, so we care about the load and we want to make sure that we're protecting the load. So when you get a start signal for a parallel system, it's all hands on deck, because you never know when a unit's not going to start. Like I said, let's say it's a 96, 98% reliable piece of equipment. That means if I started it 50 times in a year, there's one time a year on average, then it's not going to run. But we don't know which unit. So I want the entire system to run, all units on board. And then we have the ability, maybe we're a half hour in and we realize all the generators are only running at 30% load. So maybe we do shed units. And so there is built into software of some of the controllers, I can't say all of them, but some of the controllers, it'll say, yeah, which unit has the highest number of hours? Let's dump that unit and bring the average load up of the system on the other units that are remaining, save some hours on this one. some people have that conversation and say, well, they're trying to optimize this maybe for fuel consumption. But I can tell you with today's electronic engines, you're not really saving much in the way of fuel when you do that. So it's available to be done. Some controllers do it, some don't. Um, but you want to make sure that you still stay with the system that says, okay, everybody on deck. Let's make sure we have enough capacity to meet the need. And then if maybe after half an hour, we realize we have excess capacity, maybe it's at night, so we don't need the cooling as much as we did. We want to drop a unit, we can go ahead and drop a unit. And you can program and say, yeah, drop the unit with the highest number of hours on it.
Great. Can paralleling ever include mobile generators, or is the switchgear and programming too prohibitive for that type of setup?
Well, it can happen, but you've got to have, but I mean, every duck has to fall in line. Okay, so first and foremost, how big of a piece of equipment are you talking about as far as a roll-up piece? Because there's limits as to who makes what. Then it also is the commonality of controls. That's really where the problem comes in, is when you're trying, if you're mixing brands, you're already in trouble because you don't have commonality of controls. Okay, that's the first part. So if you have brand X as your stationary unit and you want to roll up a generator to tie to it, if it's not from brand X and if it doesn't have that controller on it, you're already in an uphill battle. So I'm not saying you can't, but you need to make sure you have the provisions. Like you need to own the roll up unit and make sure it's compatible. If you just call up a rental company and say, hey, send me a generator that's got a pair line controls. One, do they have it? Two, is it compatible with the stationary unit you already have? Okay, so it can be done, but a lot of things have to fall in line. There are mobile pieces of equipment that do parallel on their own to one another, right? There's twin packs and things like that that are onboard units that parallel to one another, but they were built that way with commonality of controls. That's going to be the biggest challenge.
You mentioned some flexibility in layouts. Is there a limit on the physical distance between parallel units?
Fair enough. Fair question. That's going to depend on the controller and the method of interconnectivity between the controllers. We had a controller for a long time. Our primary controller for a very long time spoke Modbus between the units. And Modbus has availability of 3,000 feet, right? I could put one generator here. I can put a generator 1,000 feet away, and their communication protocol will allow them to do that. There's a lot of copper between them, let's be fair. But at the same time, I can put them. We have a job at a VA hospital in New York. It's 5 generators. There's 3 in one place, and on the other side of the building is 2 others. They're a long way away. But Modbus allowed them to speak because they were within 3,000 feet. But if your system is an Ethernet system communication, that's going to be a challenge because Ethernet is distance limited, right, to 800 feet. If you get CAN bus is going to be limited. You can do things. We've done projects in the field where we've put like fiber optic repeaters, where we've paralleled units, and the communication wouldn't make it, and so we did fiber optic comms. That was a bit of an event. It was a little bit of a Frankenstein project. It was a unique serial number 1, but that did work. So you've got to understand what is the protocol that's communicating to the units and understand the distance. But after that, yeah, put a unit on one side of the building, put a unit on the other side. The synchronization happens at the gens. So once one unit's on, all that connecting copper is considered a common bus, right? You're not paralleling at one place, you're paralleling at the gen. So all these pieces of cable are all part of a common bus between all the units.
Okay. If you were to look at an engineering specification, what are the terms that you would see for different transition methods?
Oh, the 2 big ones, right, is going to be you're either open transition, which is, again, break before make, or you are closed transition, and that is make before break. And within the closed transition world, you would either be momentary closed transition, soft load, 5 to 30 seconds, or long term. And again, equipment wise, soft load and long term, because those are active synchronization, would be pretty much the same piece of equipment, right? Once you're paralleling more than 100 milliseconds, absolutely, it's all the same equipment. So those are the terms, right? Is open transition, closed transition, and then soft load versus long-term paralleling, right? And Open transition and closed transition are going to be passive synchronization systems, and soft load and long-term paralleling are going to be active synchronization, where we're going to control or bias the generator speed and voltage to make it match the other source.
That's all the questions we have. So just want to end by saying thank you to John Sharp for this presentation, and thank you to everyone who joined. We look forward to seeing you on the next one.